Hello and welcome to today's Connect Online session. The session will be about big data analysis with NiQL for Analytics, and I am Till Westman.
And I'm Dmitry Laichigin.
And we'll present this topic together. So let's take a quick look at the agenda. The first part will be NiQL for basic JSON querying and manipulation. So that is kind of an introduction on the topic. We'll try to keep it short and get to the interesting topics quickly. And the second part will be the presentation by Dimitri on the analytical features of NiQL. So let's get started. Before we get started with the queries, let's take a quick look at the data. So you'll see here 3 of our data sets that we're working with. The first one is the stores data set, then there is a stocked by data set and a products data set. And the stocked by data set basically connects the stores and the products data sets. And if you look at the stores data set, there's one example record that we have in here. And you will see that we have in blue here the address field, which is a nested field, a nested object, which is something that you can have obviously in NiQL because it supports JSON as a data model, but you can't have that in relational systems. So that's a little bit different from standard SQL. And the other one is the categories field, which is an array, which is another form of nesting where you nest basically values within a field. All right. Then we also have 2 other fields, no, 2 other data sets. One is the users data set and the other one is the orders data set. The users data set on the left, you will see at the very bottom, it has a field that is colored in red here, and which indicates that this field might be present in the record or it might not be present. So basically there is the concept of fields that are available or non-available, which is somewhat different from what we have in SQL where you only have null or not null. And the other data set here is the orders data set that also has 2 such fields that can just be there or not be there. And we'll talk a little bit later on how to deal with them. All right, so but first we are looking at very simple NiQL, and the main point about NiQL really is that NiQL is a generalization of SQL. And so most SQL queries work just as they are. So here you have a simple query. We are taking our users and orders data set. We are joining them on the user ID. We basically limit them by just I filter them by the total price, which needs to be greater than 500. Then we order them by the total price, and then we get the email and the time placed of the orders. And so that's what you see on the right. So basically, this is a very standard SQL query. And the result on the right also is somewhat standard SQL. It's a flat result, but it's expressed in JSON. So that is basically very normal, and you will be very comfortable with that if you know SQL. But it's not always the same. So you know we have a slightly different data model, and we allow nesting, and we don't need a schema. So there are a few differences. And so I will just give you one example of that to warn you of what could happen. So we have a query here, which basically wants to get you the orders where the total price is the maximum of the total prices that we have. And so this is a very regular query. We have the subquery selecting the maximum of the orders. And so if we want to run this perfectly valid SQL query in NiQL, we'll get an error. And well, it's a relatively simple error, and the challenge here is that what happens in this query is that the orders that you see in the subquery is interpreted to be an order, a field of the orders that you see in the from clause, which is which turns out to be an object and not a collection, and so therefore the query processor doesn't like this. To resolve this, I mean, the challenge is exactly what I just said. It's we're wrongly guessing what this field is. And so to solve this, we introduce aliases, what any SQL writer would do anyway. And so in this case, what we have done for the orders in the from clause, we have introduced the alias 01. And for the orders in the from clause of the subquery, we choose 02. And so now basically there is no more ambiguity here. And so something better might happen, but it actually gives you an empty result. So the question is, why is that an empty result? It is an empty result because in standard SQL, you would expect this to work because the standard SQL would apply the fact that this needs to be all flat data. And so it would assume that you can compare total price with the result of that subquery. However, in SQL++ or in NiQL for analytics here, that doesn't quite work because you will get a record here and you will try to compare a record with a scalar, and that doesn't work. So we need to solve this problem, and we can solve this problem in NiQL, as you might know, by introducing the value keyword into this clause. And so what's happening here is, so instead of returning a record that contains the max of the total price, we actually just get the value. And so now basically we expect that we get a value from the subquery, and we compare that with the total price, and we're trying to run this, and we again get an empty result. And which means there's still one more thing to think about, which is that the result of the subquery is actually an array or a collection. And so now we're still comparing a scalar with a collection. So to get that last piece done, we need to do one more step, which is that we want to extract the last or the first item of the result sequence to compare that now scalar value with the total price to get the right result that you see on the right. So all of this is kind of an explanation and somewhat of a warning that the language is very flexible and forgiving, and if you don't get things quite right, comparisons can return null, and that will return often in filtering them out. So there is something you need to think about if you work with this language, but it gives you a whole lot of flexibility, and this is kind of a little bit of the trade-off here. If this was a little bit too quick for you because maybe you weren't aware of these things, you can also check out the Connect 2018 presentation that we have on a similar topic, which discusses this in a little bit more detail. So this is just a short version of that warning. All right, so we've talked a lot about nested data, or at least a little bit about nested data. And so if you have nested data, you also need to think about unnesting. And so what you see here is a query that comes from an orders data set. And if you look in the from clause, you will find out that there's this unnest keyword there, which means that what we're doing here is we're unnesting an array subfield of an order, which are the items or the line items that you're working on, to basically get to a flat representation of the data. So we're taking the orders, we're unnesting the items, and from basically those combinations of orders and items, we will get the order ID, we'll get the user ID, we will get the product ID, which we are unnesting, and we'll get the quantity of that. And so the result is then something like this, where now you've basically brought the nested data up to a flat level or to the top level, and you get these results that contain exactly the order ID, the user ID, the product, and the quantity. So that is a way to get basically nested data out and bring it into a flat representation. And if you kind of don't like the unnest keyword, you can also make that a little bit simpler by just using a comma here. So what's happening here is that we in NiQL, you have left correlation here between the orders and the O.items that you see on the right. So basically the O on the left is the same as the O from the right. It binds to the same value. And so this is kind of a shorter and somewhat more elegant version of expressing this. All right, so we have nested data. We talked about that. So then there's one more thing to think about, which is that you also want to be able to do predicates on nested data. And so nested data in this context is mostly arrays. And so if you look at this query, we have what we're trying to do here is we're having the order. The order has some line items. And what we want to find out if something is true for all the items in this array inside of the order. And so the thing that we want to be true is that the selling price of each item is greater than 80. And so we express that with the query that you see here, that sum I in O.items satisfies that the selling price is greater than 80. And that works just fine. So basically we'll get a result here, and that gives us basically the user ID of all the users that had such items in their order. All right. So, and of course, if you can do that basically with this existential quantification query that we just saw here, that you basically qualify all of those orders that had some items. We can also do that for all items or for every. So basically the equivalent, or not the corresponding query here is selecting the orders where every I in items satisfies that the selling price is greater than 70, and then you get a similar result, just a little bit smaller because there are fewer orders that satisfy that. All right, next step, let's remember the data. We talked about the missing fields here, and I promised that I would talk a little bit more about that. So just a very simple thing. So we, if you have a query like this one, you will see that we're selecting here a few fields from the orders data set, and we're selecting the ones where the total price is greater than 150, and we're selecting the ones that are not fulfilled yet. And not the orders being not fulfilled means that the time fulfilled field is actually missing, so it's not in the data at all. And so when we run this query, now basically we look at the select clause and we see there are 5 fields projected here. However, if you run this query, you only see 4 fields on the right. That is because as this field is actually missing, as we have specified in the where clause, it also doesn't get created in the result records, and so therefore all of the results records only have 4 fields. So the missing property basically is used to kind of reflect the fact that it's missing, and that will be transferred to the query result in the way that it's really just not there. Okay, so these are a few basics about kind of dealing with nested data in NQL. And now let's get to the start getting more analytical, because we said this is all about big data analysis. So let's talk about aggregation and grouping, or grouping and aggregation. So one thing that is kind of interesting in a language like NQL, where you have nested data, is that you can separate the aggregation from the grouping. So in this case, we can do something which only does aggregation and no grouping, which is not possible in SQL. So this is a very simple case. We basically, again, we have users and orders, and we're joining them. And we want to get the email and the number of items that we have in an order. And the way we do this is simply that because things are, so to speak, already grouped, because there's nested data that is available inside of the order, we're not kind of having a SQL style aggregation. We just do an array count of the items in the order. And with that, basically, we can get the result of having the email address and the order size for the users in the data set. So that's a very simple way, but so that allows you to separate grouping from aggregation. So the next thing is even more interesting, which is that not only can you do aggregation only, you also can do grouping only. So if you look at this query, we again have our stores, and we have our orders, and we're joining our stores and our orders. And if you look carefully at the group by clause, you will see that there is a group by, of course, which groups everything by the state of the address of the store. But you also have a group as clause. And what that group as clause allows you to do is to actually have an instance of the data that represents the groups that you have grouped by. And so the query in the select clause, you will see basically we're selecting the state, which is what we group by, and we also select the group variable that we've just introduced with the group as clause. And so the result of this query will be the following. So what you do is, of course, you have a sequence of records, and the first record here has the first field, that's the state. And here the state is Arkansas. And after that, you have the second field, which is the group variable. And inside of the group variable, that is a sequence of pairs of stores and orders, S's and O's. And for each store and for each order, basically, you have the full record in here. So basically, this can be, of course, a very big result. So just showing basically one single object out of this. And so on the left, you see the store with all its field. On the right, in green, you see the orders. And so basically, now you have access to everything that's actually in that group. And so that is kind of interesting, let's say academically, if you kind of want to really know what's in there. But it also is very practical. So for example, you can use any subquery that you want on top of the group variable. So in this example, it's the same as we had before. We're grouping by the state, but instead of just returning the group variable, we run a query on the group variable, a subquery on the group variable, right? It's any subquery. In this case, what we do is just basically we're getting the store ID, we're getting the store name, and we're getting the order ID. And with that, basically, we get these store order pairs, and we get a result that looks like this. So where we just, again, as before, we have the state as the grouping variable, and then we have these individual pairs that we chose, basically the subset of the groups that we were looking for. And with that, there's actually one other nice thing about this, which kind of shows how NiQL is a generalization of SQL. So if you look at this SQL formulation, the SQL query that just does what you usually would do is doing this join, grouping by the state, and getting the count star to kind of understand how many stores you have, how many orders per store you have in that state. You can basically express this in NiQL in a more in a way that basically really shows what's happening inside, which is that you group by the state, you get the group variable, and then what you do in the select clause, you just take the count of the groups. So basically that gets to the number of the groups, and therewith you get the number, the count of the orders per store in that state. All right, so this was a short introduction to the topic, and now let's move over to the real analytical features of NiQL. Dimitri, please go ahead.
Thank you, Till. And I'm going to talk about advanced features of NiQL for analytics, grouping sets and window functions. Both features have been supported in standard SQL for a while. Grouping sets were introduced in SQL 99. They extended group by clause to allow aggregation over multiple dimensions. Window functions appeared in SQL 2003. So these functions allow aggregation over windows computed on the input data. We've been supporting window functions since 6.5 release of Couchbase Analytics. As for grouping sets, we're planning to support them in our next major release, so we're showing them as a feature preview today. So we'll start with discussing various window function calls, go over some examples using those, and then move on to grouping sets and related rollup and cube modifiers. Window function calls are widely supported by all major database systems. They provide a concise way of specifying aggregations over logical data partitions and windows over those partitions. So let's start with a simple window function call, computing ranking over the whole dataset. We'll use the rank function for that, followed by over subclause. So this subclause indicates a window function call. Inside the over subclause, we're providing an ordering condition. Window function evaluation in this case is the following. First, we establish the input tuple stream. And our product dataset contains a small number of documents with non-numeric values of list price. So we need to filter those documents out. Then we start processing the over subclause. We order all input tuples by their list price from greatest to least because we have a descending modifier in the order by. Then we go through those ordered tuples one by one and assign the rank incrementing from 1. If a tuple has the same list price as its predecessor, then we do not increment the rank. We skip over that rank value until we find first non-equal successor. That's why there is a jump from 5 to 10 in the rank value of the last item. In previous query was combining computing rank over the whole data set. But what if our goal is to establish ranking within each product category? We could achieve that by using partition subclause. Partition subclause instructs the query processor to partition the input tuple stream into non-overlapping logical partitions, then evaluate the window function independently on each partition, ordering partition tuples before computing the functions. As we can see in the query results, in this case, we have multiple products with rank 1, because we started with that value in each product category. Recall also that the rank is the same for products with the same list price. That's why we have 3 top-ranked beverages in the result. Logical data partitioning performed by window functions gives us a flexible way of filtering data within those partitions. In this example, the rank is computed by the subquery and used by the main query to return only the top products in each category. Notice that the subquery is written as a common table expression using the with clause. This is another SQL feature that is supported in NiQL. Common table expressions make queries modular, easy to write and debug. As you can see, we have query results ordered by rank, and we only get top-ranked products in each category. So far, we talked about special window functions like rank. But any regular aggregate function can also be used in a window function call. Aggregate functions, however, need a list of values to operate on. So therefore, when an aggregate function is evaluated in the context of a window function call, there is an additional subclause in the over clause that defines a frame of tuples for it to process. You had probably seen it before in SQL queries. It starts with rows or range and could be bounded or unbounded, preceding or following. It is optional though, and if not specified, then there is a default one that would be used. We support exactly the same frame specification in NoETL with the same defaults. The evaluation steps are then augmented by the new frame computation step. The first two steps remain the same. The input tuple stream is logically partitioned, then tuples are ordered within their partitions. So each partition is then processed independently of others. Couchbase Analytics is able to process them in parallel if the system has enough resources. The evaluation starts at the first row of a partition and computes a frame of tuples for that row based on the given frame specification. Interestingly enough, the frame may or may not include the row itself, because the purpose of the frame is only to provide input to the aggregate function. Then the aggregate function runs on that frame and computes the result, which is added to the output. After this, the query processor moves on to evaluate a second row in that partition. The frame is recomputed again for the second row, and the aggregate function is reevaluated on that frame, producing the second result value. Then the evaluation moves on to the third row, and so on, until the whole partition is processed. Frame specification syntax is quite elaborate and gives plenty of room for query optimization opportunities. A frame could be static, so its contents doesn't change from one partition row to another. Some frames could be sliding, while others can have a fixed starting point and just keep growing within a partition. This variety allows the query processor to employ optimal execution strategies for different frames. Coming back to our example, there is no frame specification given in the window function call here, so the sum function will use the default frame specification, which is range between unbounded preceding and current row. This frame specification corresponds to a running total computation. The query intent is to produce monthly sales in 2020, along with the running totals. So in order to achieve that, it first aggregates sales by month and then uses the window function call to compute running totals over those aggregated values. And one more query example before we move on to grouping sets. This is a very common analytical query. We would like to produce a report showing our annual sales growth broken down by quarters. In other words, how our sales are doing each quarter this year as compared to the same quarter in previous years. So in order to produce this report, first we need to aggregate orders by year and by quarter within each year. That's what the subquery is doing. Then it's time to apply a window function on top of those aggregated values to compare each quarter with its predecessor from last year. The window function call we'll use is called lag. Note that it's not an aggregate function. It simply provides access to a previous value in the logical partition, produced by partition by subclause. And that's exactly what we need here to solve the problem. We partition subquery results by quarters and order by year within those partitions. Then we use the lag function to access the previous value, sales value, which is the quarterly sales in the previous year. Once we have that value, the rest is straightforward. Notice that we have now for the first sales growth number in the query results. This is because we only have sales data starting from 2018. The lag function returns null for the first row in each partition. Hence, our growth computation expression also returns null. Now let's turn our attention to grouping sets. As I mentioned earlier, grouping sets have been supported by major relational database systems for a while. And we're also working on adding them to NoSQL for analytics in the next major release. Let's look at the following query. We would like to count the number of stores in each city in each state. To limit the results, we would only consider states with names starting with C, so just California and Colorado. In addition to count by city, we would also like to get a total count by state and the overall count of all our stores. How do we do that? One way of implementing this would be to have a union all over 3 subqueries. The first subquery would group by state and city. The second would group by state, and the third one would just do select count star over the whole dataset. That would work, but requires a lot of code duplication. With grouping sets, we have a better way. We can simply use a rollup modifier in the group by clause. If you look at the box on the right, you'll see 3 different formulations of the same query. The main actor here is the grouping sets modifier in the middle, which provides a compact way of specifying those unions. Each grouping set is logically expanded into a separate subquery, and they're all connected by union all operations. Of course, this is just a logical way of describing the result. The query processor is free to optimize the query, and in some cases could find a faster way of computing the same result without subquery expansion. So the grouping sets modifier is a shortcut for union all, but the rollup modifier is a shortcut for grouping sets. Rollup with n elements is expanded into n+1 grouping sets, rolling up to the grand total. So in our query, we start with a rollup with 2 elements, state and city. Therefore, it would expand into 3 grouping sets: city state, the whole state, and the grand total. And that's exactly what we want in our report. If we look at the query results, we'll see black rows that correspond to grouping by city, blue ones for the whole state, and the red one for the grand total. Cube modifier is a relative of rollup, but performs a slightly different expansion into grouping sets. So in this example, we want to find out our total sales by each year within each state. In addition to that, we would like to roll up by year, also roll up by state, and get a grand total. That's what the cube modifier is for. It can roll up by multiple dimensions. Contrast this with the rollup modifier we discussed earlier, which can only roll up by a single dimension. If we look at the cube expansion on the right, we'll see that given n elements, it produces 2 to the power of n grouping sets. So for 2 elements, it would produce 4 sets, for 3 elements, 8 sets, and so on. Recall that each grouping set is logically equivalent to a union all subquery, so the cube modifier saves a lot of typing. As for the query results here, in black color, we get total sales grouped by state and year. In green, grouped only by state. In blue, grouped only by year, and a single red row for the grand total. So this concludes our short overview of advanced analytical features in NoSQL for Analytics. Now back to you, Till.
Thank you, Dimitri. So if you are interested in more information about NoSQL for Analytics, there are 2 excellent resources. One of them is Don Chamberlain's book, SQL++ for SQL users, which gives a great insight and great explanations on how NoSQL for Analytics works and what's interesting about it. And of course, there's also the NoSQL for Analytics query language tutorial on the Couchbase website. With that, I would like to thank you for your attendance of this talk and hope you will have a great conference. Thank you.